This is part 2 of Project Big Ben, and this one looks at the motor drive assembly for the clock hands. These are the concentric tubes for driving the 3 hands, hours, minutes and seconds, and these are turned by 3 stepper motors. That would have been a lot easier if the motors had hollow shafts, as they could be directly coupled to their respective tubes and stacked one behind the other. But these are not very common, so I settled for standard CNC motors and had to accept there would be some sort of coupling. Now the coupling needs to have minimal backlash, which put me off making or sourcing gear wheels, so I chose a belt drive. Again, these parts are readily available from the CNC marketplace. So the plan was to offset each motor from the shafts and mount them onto a frame using slotted holes so the belts can be fitted and tensioned. Now, this caused some further head scratching, as I needed to add some feedback sensors so the controller would know where the hands are. The clock has to be able to recover the correct time after a power outage, or if the hands are moved or knocked accidentally. The first plan was to use simple on-off sensors like these. For example, a Hall effect sensor could detect a magnet mounted on the motor shaft or on the hands themselves. Another option could be an optical sensor. This one triggers when the beam inside the slot is interrupted. Now either of these would be fine at power up, as the controller could step the motors till the sensor position was reached, and then reset its step counter. The disadvantage is that if anything happened while it was running, the time could only be corrected when the hand reached the reference point. Maybe not so bad for the second hand, but definitely unacceptable for the others. Luckily, I discovered these amazing AS5600 Hall effect chips, which can measure rotational angles. You could just fix a magnet to the end of the motor shaft, place the chip a couple of millimeters from it, and the controller would know exactly where the hands were at any time. These sensors have many other uses. My first thought was to replace rotary encoders, which have a habit of failing after a period of time, and this one would have no internal contacts, so it will never wear out. Now, if you do try them, be aware that the magnet has to be polarized the correct way. And that leads on to yet another Victor Meldrew moment. Where would we be without these? Just glue the magnet to the end of the motor shaft. Piece of cake. I didn't have any instant acting superglue, but no matter, I thought. The still shaft is magnetic, so the magnet will hold itself in place while the glue sets. Wrong. Conventional disc magnets like these have poles on opposite faces, and these are no problem. But it turns out they will not work with this sensor, as the north and south poles would not be moving. You need a magnet with the poles on opposite edges, like this one here, and when you place this one on the shaft, it immediately tries to flip itself onto its edge. I don't believe it. So I had to make this little holder to keep the magnet flat, and it also helped to centralize it, so it was probably worth it after all. And the chip has some tolerance to off-center wobble, but it's better to eliminate any doubt right from the start. The magnetic gap is also fairly critical, so the chip and motor are both mounted on a smaller subplate, so they stay aligned when the motor is moved for belt tensioning. And using a sub-assembly also means each sensor can be calibrated and checked before fitting to the frame. I'll just plug this one into a test controller, which is programmed to read the chip's status registers and display them here. I've taken the screws out just for demonstration so I can move the sensor around. The first LED shows a magnet has been detected. Now the field strength depends on the magnet itself and also its distance from the chip. So there are 2 other status bits. The second LED shows if the field is too weak, and the third shows if it's too strong. The chip also has a built-in automatic gain control, or AGC, so there's some tolerance to variations. This AGC value can be read, and this is shown on the left-hand 4 digits of the display. The range depends on the supply voltage, and on 5 volts it goes from 0 to 255. And the spec says to adjust the magnet so this value is in the middle for the most robust performance. And I can do this by adding washers to either of these points. The rotational angle is a value from 0 to 4095, and this is displayed on the right-hand 4 digits. I'll turn the motor by hand, and you can see there's plenty of resolution for this application. There are many other features in these chips, but I don't think I'll need them. Right, this one seems okay. I must remember to fit the belt next time, so I'll make up the other two and continue in the next video.